So to begin the panel, I'd like to call up Professor Dr. Henri Safa, who is from France, and he will be speaking on why nuclear energy of the future is the only solution to tackle the world's growing energy demands. Professor Dr. Safa.
Good afternoon. I would like just to show you this afternoon why nuclear appears really unavoidable in the long run. And first, if we take from the historical perspective, you know that energy has always been important for humanity, and we started using biomass for a long time ago. And so biomass was the first we have been using since very, very long time. And when coal has been discovered in the 17th century in England, it has really changed our world because it has led to the industrial revolution that we have in the 18th century. And afterwards, of course, discovery of oil in the 19th century has led to the tremendous growth that we have in the world in the 20th century. And this has eased basically all connection in the world, transportation in the world. And afterwards, of course, liquefaction of gas in 1956 has also did a big burst in the energy that we are seeing already today in the expansion of energy use. At the same time, electricity, when we started using electricity on Niagara Falls, this was astonishing also use of energy, of transportation of energy over long distances that can be used easily through only a small wire, a small copper wire. And this has led also to the use of energy on long distances. And everybody knows that in 1942, Fermi has built his first pile in Chicago Stadium. And this was very astonishing that he could, at the very first time, extract energy from uranium. And this has also been expanded in the late 20th century. So just a few basic figures, just to have in mind what is the amount of energy we are talking about. Of course, the official unit is joule. But the more common unit is kilowatt hour. This is what you use every day. And 1 kilowatt hour, just to make things in mind, is 40% of what we need per day for a human body, but it's only driving 1 kilometer in a car. So it's a fairly good amount of energy. And for example, if we want, we just want to go and take a baguette at the bakery store, sometimes we are moving 1 ton of metals over kilometers just to have this movement of 250 grams. So this means that one point I wanted to stress here is the efficiency of using our energies. And this is very important. Another thing that has been discussed also over the centuries, especially by James Joule, is that energy, in fact, doesn't appear from nothing. It is only converting energy from one form of energy to another form of energy. So energy doesn't disappear. Energy is a conservative physical unit. And what we are just doing is, when we are using energy, is that we are just moving one form of energy to another form of energy. And this is what Jules has shown with his small apparatus here, where he had the small mass here falling with gravity. And this mass is connected to this small water loop where we have pails here rotating in the water. And he has just shown that energy from gravity is transformed here by energy by heat in the water, and he measured the temperature. And this is how we determined that we need 4.4 joules to heat 1 gram of water by 1 degree. And this means that after that, the idea has been to convert energy from one form to another, and we invented a lot of techniques to convert one energy to another. Of course, we have thermal energy that everybody knows. We have chemical energy, electrical energy, mechanical energy, and radiation energy, nuclear and hydraulics. And for example, when you are lighting, when you have lights in the lamp, you're taking electrical energy in a resistor, you're heating the resistor, going to thermal energy, and then this thermal energy is at a sufficiently high temperature to have a radiation energy. So you're moving from this part to this part to this part. Only when you're doing that, the overall efficiency going from electrical energy to radiation energy is only 2%. So this means that you're losing 98% in the process. And this is why it's important to have efficiency in the process. When you're using nuclear energy, you're going from nuclear material to fission, doing thermal energy, going through a turbine, heating water, mechanical energy, and then going to electrical energy in an alternator. So you're moving these 4 forms of energies to go to electrical energy. The other main issue here in using energy is density, is energy density. When we discovered coal was very interesting. Why? Because it has 2 times the energy density of biomass. And this allowed to make trains running on steam. Because we could put enough coal in a train in order to move the engine. So, and when we discovered oil or gas, which is the most dense energy that we know for the moment as chemical energy on Earth, it has been even more used and more sought for because it is even 3 times more dense than biomass. And what is important here to see is that for uranium, because it is nuclear binding energies, it is 100,000 times more dense than petroleum. From this fact, I think that it is clear that we need to use this tremendous amount of density of energy. This factor, 100,000, is very important for us because we can use very little mass from the Earth to get the same amount of energy as burning oil. 100,000, you have to bear in mind this figure of 100,000. This means that this simple fact will tend to say that the human being will be using nuclear energy in the future as his main source of energy. Now, if we look at the world energy consumption today, you see that we are, of course, there has been a tremendous increase of use of energy in the Earth, only because, first, the population is increasing, but also the wealth and the growth, economical growth of energy is demanding more energy. And we are at this time here you see that what is important here in this figure is that through the discovery of the different energies, we never left over other energies. There have never been substitution of energy. There have been always adding more and more energy to what we know. You see that even today, the biomass, which is the old use of energy from humanity, is still increasing. Coal is still increasing, petrol, oil also. And by the way, you see that renewables here are in green is less than 1%. So all this energy are increasing, and the people are asking for more and more energy. Why? Just because energy and growth are intimately linked together. We cannot get human development without energy. It is clear that if a country wants to develop, it will need enough energy per capita here to develop in order to be on the right side of the curve, which is this side of the curve, is developed countries. So many countries in the future will have to develop to the level of the wealthiest countries, and will have to have at least 4 tons of oil equivalent per capita in order to be enough developed. This means that we can foresee right now that most of the world energy consumption will continue to develop in the future. Now, I will skip this electricity prices issues and go directly to the energy sources. So if we want more energy, where can we get these energies on Earth? As you know, we have the fossil fuels energies that we have discussed just now, coal, oil and gas, and we have the renewables energy, hydraulics, wind, solar, biomass, geothermal. Most of the renewables are coming from the energy from the sun radiation, except for the geothermal. And we have nuclear energy, which has been formed at the beginning of the formation of the Earth, 4 billion years ago, where we have this uranium has been formed from the beginning in the Earth's crust. So these are a very long time. This has been, we needed very long time to form these kinds of fossil fuels, 100 million of years. These are basically diffuse and intermittent energy sources. So we need something that can last sufficiently long as resources, and we need something that is not intermittent and diffuse, which has sufficiently energy density to work out enough power. If we look at the resources, the present world resources, basically oil and gas resources, if we add even additional unproven resources, will last probably in the hundreds of years. This means that in the next century, these will be very, very expensive because they will be rare. We will have to get them deeper in the ocean or far to get access to these resources. Coal is more common, and we have much more coal on Earth than we have oil or gas. So basically, coal will be extensively used, and it is a resource used now, essentially in China. It's a basic resource in most countries now, is coal. And if we use uranium as we are using today uranium in present reactors, we only have for 300 to 400 years of resources. So this means that if we want to use nuclear energy on a longer period of time, we will have to use new kinds of reactors to have enough resources to last sustainably longer than that we are today. So just a few words about uranium resources. Because of this factor 100,000 I talked before, this means for the same amount of energy you see this small nuclear pellet that we put in the reactor, 7 grams, is given as much energy as 5 barrels of oil. So this means that we need very, very low resources for the same amount of energy, as instead of getting billions of tons of oils, we only get thousands of tons of uranium. So this factor of 100,000 is very important from the point of view of resources that we got on Earth to access. Energy independence, low cost, low quantity of waste produced, and low environmental impact. We can get to these if we had to discuss more. So what are the prospects now for the future? For the short future, for the long future? For the short future, we have today to enter a new era where we have to modify the energy use that we are doing today. And some energy rules can really be game changers in the energy consumption on Earth. The first of them is the energy storage, very important. Today, we do not know how to store electricity. So we have to produce electricity at the same time we consume it. And this makes a very stringent very stringent operational things for electricity. The second game changer I will talk about is recovery of wasted heat from our energy, from our electricity plants. And there is plenty of heat to recover there. Electric transportation, and the fourth is the longer-term sustainable energy for the future. So, electricity storage, the only storage, large storage, I'm speaking about terawatt-hour storage, not the small battery of your computer, which is 100 watts. Large energy storage, the only usable large energy storage is pumped storage hydroelectricity. So when you have electricity in excess, you can pump the water in a storage to the upper part of the dam, and then when you want to use it, you just release it by mechanical weight. And this can be done only in countries where you have mountains, of course. It's very difficult to do elsewhere. Other kinds of electricity storage are the compressed earth storage beneath the ground, inertial wheels, where you just spin the wheels at high velocity and then you try to recover. Of course, batteries and superconducting magnetic energy storage. All these are studied in the labs, but none of these are applicable at high energy and high power. Other kind of energy storage, the thermal storage. Here you have a house or a complex where you can store energy in summer and recover it in winter. You have the chemical storage, which is the best storage we can know is your storage in your car, for example. And you have the fuel cell storage of hydrogen. But when you put the figures in of all this kind of storage, what we need to do is to have enough power in this storage. This is a pumped storage hydroelectricity. So you want to be in the upper part here in the 100 megawatts regime, and you want this storage to be not very expensive. So you want to be in this part of cost. That you see that most storage available is low power and high cost. So there is plenty of work to do in order to make these kind of storage go in this range. So this is the challenge for the next 30 years. The second challenge is the recovery of electrical power plants' heat. Why is that? Today, when you make this transformation, I told you that all we are doing is converting energy from one form to another. When you're producing electricity in an electrical power plant, here is, for example, a nuclear power plant where you're heating the primary water in the core of the reactor and transforming it to electrical power. Only 1/3 of the energy released from fission is transformed in electricity. And 2/3 is just lost in the environment, heating the birds or heating the fish. And this is not very good. So this is one example in our reactors in Nogent-sur-Seine, where you see that all this heat is going to the atmosphere. So what we can do? What we can do is we can change the system in the secondary loop of the reactor in order to recover this heat, and we can use this heat to go and heat the cities. The problem is the nuclear power plants are generally far from the cities. So the problem is how to transport heat, long-distance transport heat, hundreds of kilometers, 150 kilometers from the nuclear power plant to the cities. And this can be done today with very low losses. We can have 150 kilometers transport line with less than 2% of lost heat. And we have programs where we can try, let's say, to recover the heat from Nogent-sur-Seine nuclear power plant and to try to feed it in Paris city, 120 kilometers away. And Paris has already a district heating network, which is the largest in France, and it has been there for almost a century. It started with trains in Gare de Lyon, where we tried to heat the vapor in Gare de Lyon, and it's still there, still working. And for the moment, this heat is used with coal power plants in Saint-Ouen or with gas power plants. And if we can take nuclear heat, this can save a lot of energy and a lot of money for this. The third challenge is the electric transportation. Why electric transportation? What are the advantages? If you take an internal combustion engine, you have 33% efficiency in the engine, and you have only 20% converted in motion of the car. So this means that you are losing 600 watts per hour per kilometer. If you go to an electric car, you're only losing 200 watts hour per kilometer because the electric engine has an efficiency of 90%. So this means that you gain 3 times less energy for the same motion, and also you have no CO2 emission at all. So fourth challenge is the long-term sustainability of nuclear. And this is basically sustainability is driving what we call the design of new reactor systems, where we are using uranium, the uranium resources, much more efficiently than what we are using today, 50 times more efficient. So how we do that? So this is only the uranium resources that we have on today for this price. And what will happen if you are using present nuclear reactors? You're just consuming our uranium all along here, and you see that in 50 years from now, we will hit our maximum resources that we have at a given price. So we need to do something in order to move to new reactor, what we call fast reactor. If we introduce them early, we can have enough energy from this fast reactor to last a very long time. And what I say long time is tens of thousands of years. So it's a much longer time scale than what we have today for our reactors. The resources needs for fast reactors are only 8 tons of depleted uranium as compared to 200 tons of natural uranium that you need for our present reactors. This means that the gain we can get from there is a long-term gain sustainability for the nuclear reactor. And this by itself justifies developing these new nuclear reactors for the long term. So I will just skip the actinides and go for these kinds of reactors that the people are thinking about today in the world. There is an International Generation 4 Forum that has been started in 2000, and where we have selected 6 types of fast reactors for the future. One type is a sodium fast reactor, the other is a lead fast reactor, the gas fast reactor, the high temperature reactors, the supercritical water reactors, and the molten salt reactors. And I think that you will hear after me basically on one of these, which is the molten salt reactors. Today in France, essentially in CEA, we're working basically on 2 kinds of reactors. The sodium fast reactors, because we have a lot of experience. We have 30 years of experience in working in sodium fast reactors. And the gas fast reactor, which is more challenging because it's a helium-based fast reactor that has never been built until now. So these 2 are on a prototype of sodium fast reactor will be built in the next 10 years in France. So conclusion, basically energy density is the key issue for using future source of energy on Earth. And we need, of course, energy because we need to have economic growth, that they are intimately linked. And the game changer that we see in the next 30 years are basically the storage, electrical storage, the heat recovery from power plants, and the electric transportation. And for the longer term, I would say nuclear reactors is unavoidable for the longer term. Thank you.